Thanks, everyone. I liked Kate's keynote so much that I, too, am having voice issues this morning, so bear with me on this. Okay, we had unprecedented good fortune in submitting AIIDE papers this year, and the organizers were kind enough to put all of our papers into one giant session. And what that means is for the first half of the first paper, I'm going to introduce what narrative planning is, and then you don't have to see 7 more versions of this. Okay, so before we get into the first paper, what is narrative planning? The Narrative Intelligence Lab at the University of Kentucky builds interactive narratives for video games and training simulations. And these narratives have some kind of strict authoring constraint. So we have some kind of ending that we need to achieve or some kind of content that we need to include. But we also make the player one of the characters in the story, and we give them a lot of freedom for what choices to make. And when you put a player into your story, they make strange, unexpected choices that screws up your beautiful story, and then you have to rewrite it with an algorithm. And that's what a narrative planner does. So story generation algorithms can be placed on the spectrum from strong autonomy to strong story. On the strong autonomy side, we have multi-agent systems like Dwarf Fortress or The Sims. Every agent is its own lightweight simulation. It reasons about its own intentions and beliefs. They're very realistic, but there's not any kind of like overarching story or author guidance. On the other hand, we have something like a classical planner. And this one cares only about the author goals. It's going to find a sequence of actions to get there, and it has no reasoning about the individual intentions or beliefs of the characters. A lot of storytelling stuff is in the middle somewhere. So a drama manager is like another agent you can add to a multi-agent system that sort of tries to herd cats and make some authorial goals happen in a multi-agent system. And then the stuff that we work on, narrative planner, is a planner. But it has some built-in reasoning for the intentions and beliefs of the characters to try to make sure that the actions that happen seem realistic. I think this is a really interesting problem because technically it's a single agent problem, and that agent is omniscient and omnipotent in this virtual video game world that we've created, but it has to produce solutions that look like they came out of a multi-agent system where every agent has limited observability and knowledge. For all these papers, we're going to be using Sabre, which is the narrative planner that we wrote in our lab. That's QR codes for the code itself and for a bunch of benchmark problems that we collected from our previous papers and other work in narrative planning. So what is a narrative planning problem? What are the pieces of the problem? First, we have an initial state that says like where everybody is, what items they have, what their health status is, their relationships, that kind of stuff. Every character has a utility function, so higher utility is better. This describes what states the characters would rather be in. We also have an author utility function. So this tells us like what states the author would rather the world be in and what stories are good for the author. And then we have this database of actions. Actions have preconditions that have to be true before the action can happen. Effects that change the world in some way. Consenting characters, so we mark these actions with which characters are taking them. And those characters have to have some reason for why they're going to take the action. And observing characters, which means who's going to notice the action happening. The solution that a narrative planner gives you back is a plan, which is a sequence of actions where it can be executed. So it has to be a sequence of actions where the preconditions are satisfied when they happen. It needs to improve the author's utility. And every action has to be explained for all of its consenting characters. What does that mean? That means the action is the first step in a plan that the character believes they can take, even if they're wrong, that they think will increase their utility, and which doesn't have any redundant or unnecessary actions in it. So if we want to visualize this space, we can imagine all legal action sequences. We can imagine all the action sequences that characters believe, maybe wrongly, are possible. All the action sequences that would actually contribute to improving an agent's utility. And we're basically claiming that this purple region is the sweet spot. That's where the believable plans lie. So the actions that characters believe they can take that will improve their utility. I'm going to introduce an example problem that we're going to use in many presentations today. If you've been at an AIIDE in the last 10 years, you've probably seen this problem before. So you are the player, you're Tom, you start off at home. Your grandmother has given you her last gold coin. And she is sick, and you have to go off and get some medicine and bring it home. So your goal is to come back home with the medicine. Fortunately for you, just down the road, there's a crossroads which leads to a market. And at that market is a merchant who happens to be selling some medicine and wants money. There's also a town guard who wants to punish lawbreakers. And unfortunately, on the other branch of the crossroads, there is a bandit who wants valuable stuff like money and medicine and this kind of stuff. All right, so here's an example of a story we can't tell. This is not a valid solution. If the merchant just walks to your house and hands you the medicine. That's the kind of story you might get out of a classical planner. It achieves the author's goal, but it's not intentional, right? The merchant doesn't donate stuff. Maybe she doesn't even know where you are. We can tell this story. You walk to the market and you buy the potion and then you walk back home. So that achieves the author's goal, and also every action kind of makes sense for the characters who did it. Another possible story that we can tell is something like this. You're on your way to the market, but before you get there, the bandit shows up and steals your money. So this is another story that's acceptable. We know why you were going to the market, even though you never made it. We know why the bandit came and stole your money. Here's something we can't do. The guard can't run in and kill the bandit for you, because the guard didn't know that happened. The guard's in a different location. Guard didn't see this happen. So that sort of thing is not allowed. Okay, so now that we've kind of introduced what this is, we're going to get into the first paper, which is Detecting Duplicate States is Worth It in Narrative Planning with Belief. All right, back to our problem. Here's the story we're going to look at in this paper. You don't know that the bandit exists, or you don't know where they are. So you, the naive player who's playing this game for the first time, doesn't know about the bandit, but the bandit knows about you. The bandit goes to the crossroads and waits. As soon as you show up to the crossroads, the bandit steals your money. That's the example story we're going to be looking at. Before I can show you what that looks like in Sabre, I need to talk just a little bit about what the state space graph looks like. Sabre is a state space planner, which means it's generating this giant graph, and all the nodes in that graph are world states. And we have two kinds of edges in this graph. One of them is called a temporal edge, and that's just represents an action happening. So like in state 0, the precondition of that action is satisfied. And then in state 2, that's the state the world would be in after you apply the effect of that action. But because Sabre models character beliefs, we also have this other kind of edge, which we call an epistemic edge. An epistemic edge means that, like in state 0, that blue character believes the world state is actually state 1. And Sabre has the requirement that for every character, every node must have exactly one outgoing epistemic edge for every character, even if that edge is just a loop back to the same state. So what this means is that characters can have wrong beliefs, but they cannot have uncertain beliefs. So you cannot believe many things are possible. You always commit to one particular set of beliefs, but those beliefs might be wrong. That's kind of a weird set of features. Why do we pick those set of features? This would not be good for building a robot in the real world, but we're not building robots in the real world. We're telling stories in a virtual world that we control. And we found that this set of features works pretty well for most of the stories we want to tell. Put a pin in that for one of our later presentations. Okay, so here's the story that we just told. The bandit starts at the camp. You start at the house. You've got some money. Your beliefs are you don't know where the bandit is, but you know you're at the house. And also, we just assume that the beliefs going out of that state are loops. Okay, the bandit knows what's up. The bandit knows where they are. The bandit knows where you are. The bandit knows you have some money. So the first action was the bandit walks to the crossroads. So when that happens, the bandit's location changes. They're now at the crossroads. The bandit is an observing character on that action, so the bandit knows that the state has changed, so their beliefs also update. The bandit knows they're at the crossroads, and they know that they know they're at the crossroads. But the bandit knows that you didn't see that happen. So the bandit knows that your beliefs are the same as they were before. They have not changed. One of the neat things about this graph is we have an infinitely nested theory of mind, right? So I can ask, like, what's true? What does the bandit believe is true? What does the bandit believe that you believe is true? What do you believe that the bandit believes that the bandit believes that you believe is true? And so on. You just keep following these edges, and even if they're loops. Okay, so now when you walk to the crossroads, you know that you walk to the crossroads, and also, hey, you see the bandit is here. So you update your beliefs. So now everyone agrees that everyone's at the crossroads. And then when the bandit steals your money, both characters see that happen, so everyone agrees that, oh, now the bandit has your money. Now, what you might notice is that these groups of 3 are all exactly the same state, which means if we were clever about how we represented this, we could redraw the graph like this and save ourselves a little bit of space and maybe also a little bit of time. So that's what this paper is about. We're asking, can we efficiently detect duplicate states, and does detecting and removing duplicate states actually save some time? And you might guess from the title of the paper that the answer is yes. just a quick note, in like a classical planning system, detecting duplicate states is quite easy because a state is just like an assignment of values to all the variables. So you can just hash that, put all your states in a hash table, and very quickly and like amortized constant time, look up whether a state has already been generated. It's not so easy in a system like this, which has this map of beliefs. And that's because for two states to be the same, every fluent, which is like a state variable basically, every fluent has to have the same value, but also all the character beliefs have to be the same. And the beliefs about beliefs have to be the same. And the beliefs about beliefs about beliefs have to be the same. And so on. So what that means, you might look at these two states up here and say, oh, hey, those are the same state also, so I could just like group those together into one state, but they're actually not the same state. And the way we know they're not the same state is in S0, Tom believes that the bandit does not exist, but in state 2, Tom believes that the bandit is at the camp. So even though they kind of look like they're the same state, they're really not because some of their beliefs are different. There is at least one proposition that these two states would disagree on. Is this proposition true or false? Okay, so we presented a really simple, it's not trivial to detect duplicate states, but it's also not super hard. We give an algorithm in the paper. It takes as input two states, and also this empty list that I'll talk about in a minute. And the output is true if those two nodes represent exactly the same state, and false if they don't. There's one little piece of notation you need to read this, which is beta CS. That means the state that character C believes is the state when it's actually S1. So that basically represents an epistemic edge in the graph. So here's our pseudocode. It's pretty simple. This first or second base case up here says, if we can find some fluent that has a different value, then they're definitely different states, so return false. Otherwise, for every character, we're going to check the beliefs of those characters, and we're just going to recursively call the same algorithm. So eventually, we'll check beliefs about beliefs, and beliefs about beliefs about beliefs, and so on. And if those all end up being true, then eventually we'll return true. The only like slightly complicated part is we've got this list of state pairs, and before we do that recursive call, we're going to add our current pair to that list. The reason that we do that is so that we never visit the same pair of states more than once to avoid infinite loops. If you want to read the paper, we've got a proof that this does actually work. And we've also got a proof that this runs in time polynomial to the size of the graph. Here's a quick sketch. Basically, in the worst case scenario, you're going to have to check every pair of states. But that's only n squared, right? That's polynomial time. And thanks to that list of state pairs, you're never going to check the same pair twice. So the theoretical worst case is n squared. In practice, we usually check a lot fewer than that. So we also did some empirical experiments to say, well, you know, does this actually help? Does this really save some time? So we developed two different versions of Saber's basic search algorithm. Tree search, this is how it actually works. If you go download Saber right now, this is the algorithm that it uses. The alternative is graph search. So in tree search, we don't bother to detect duplicate states. We probably generate a bunch of duplicate states. We don't bother to check that, and we don't care. In graph search, we do check to see if we're generating duplicate states. And if we do, we delete the duplicates and move the edges around to point to just the original version of that state. You might say, obviously, graph search is going to generate fewer nodes, but that's not really true. The thing with tree search is we only make a node when we need it. So we wait for someone to ask us for that node, and then at that moment, we create the node and figure out what the beliefs would be. In graph search, we actually have to generate a whole bunch of nodes because we've got to check beliefs about beliefs and beliefs about beliefs and so on. So because of that, it's actually theoretically possible that graph search might make more states than tree search. But it turns out it doesn't. So we did a really simple experimental design. We took all our benchmark problems and we just generated the state graph in a breadth-first fashion for both tree search and graph search. And we measured, hey, how many nodes are in that graph and how long does it take to make? There's a bunch of graphs in the paper, but they all look kind of like this. So tree search, that orange line is showing you that basically, and what we just ran these things until they ran for 24 hours. So at 24 hours, we just stopped it. So at 24 hours, tree search was able to get to depth 4 in that graph, but graph search was able to get all the way to depth 8 in that graph. So lower numbers are better here in these graphs. So for every single example, and it's like rare that we get such a slam dunk conclusion like this, but for every single benchmark problem that we tested, graph search generated fewer nodes and it took less time to do it. Okay, so there's one big limitation to this work, which is Saber has that weird set of features I told you about where we allow, we don't allow uncertainty, but we do allow wrong beliefs, right? So if you did allow uncertainty, like say Egger and Martin's a starry system or something like that, now detecting if two states are the same is a graph isomorphism problem, which is an unknown complexity class, but probably quite hard. So if you were to add uncertainty into this, would it still be worth it? I don't know, future work. Special thanks to my co-authors on this paper and to the National Science Foundation and Army Research Office for funding this work. That's the link to our artifact if you want to go download our experiment where we generate these graphs and measure the results that are in the paper. And now I will take questions.
I have one. Character beliefs in states are an interesting part of what yield, like interesting character dynamics. But so is the trajectory to those beliefs. Do you preserve those trajectories? Would it be worth proving them as well? How do you handle that?
I think this is going to answer your question. The nice thing about the graph having both temporal and epistemic edges is you can ask questions that cross both types of edges. So you can say, what do you believe? But you can also say, what will you believe after this action? Or after these two actions, what will you believe is possible after this third action? So you can take any arbitrary path of actions or beliefs to ask like combined temporal and epistemic questions.
In the compensation of these states who are not pruning edges that are unique to those states.
Not pruning edges that are unique to those states.
Edges to those states.
I'm not sure I fully understand, but what we do is our graph has no duplicate states in it. And the way that works is we just, every time we add a new state, we just check it and say, hey, is this a duplicate? And if so, we delete it. And all the things that we're pointing to that new state point back to the original state instead.
On your graph, like here's how the opportunities were, all these metrics. When you describe like, hey, it's got to a depth 8 or depth 4, what does that actually be?
Yeah, so we start in the initial state, and then we look at every action whose preconditions are satisfied, and that gives us the possible like second states in the story. And then for each one of those states, we look at every action whose precondition is satisfied, and that gives us all the possible third states in the story. So if we got to depth 4, that means we generated every possible state that is within 4 actions of the initial state. So basically every legal 4-step story that could happen. And actually we got a little bit farther, but that just means we didn't complete depth 5 before it timed out. So we finished depth 4 and we didn't finish depth 5 before it timed out. 24 hours per level, so it's like once you finish a level, then your like timer resets. So that means it took more than 24 hours to generate depth 5.
Practical long-term applications, narrative planners in figuring out what it says, long-term filtering, or getting
Yeah, you know, the big problem with narrative planning is it's super computationally expensive. Like it takes a long time to run if you want to tell a long story. So this lets us tell longer stories. We can explore longer stories with less memory and less time.
I'm mostly familiar with like month cover research or fast search, and it really depends on the game.
Yeah, exactly. It depends 100% on the domain. So if the domain has lots of actions and lots of actions are possible in any state, then it has a really high branching factor. And if it has, like there's at least one problem on here that's like a tiny little test problem, and we can generate like arbitrary depth. Like we can generate to depth like 500 in 5 minutes or something like that. But like some of these problems are big. And so graph search was always better, but like how far we could go depended a lot on what problem it was. Some problems are really big and some problems are small.
I wonder if it would be valuable to distinguish domains for like between, I guess, their like temporal branching factors or like aesthetic branching factors. But I feel like a game where everyone knows what's happening should be simpler in some sense than one where you can have a lot of incorrect beliefs.
Yeah.
So, like quantifying that can be helpful.
So the temporal branching factor is always a constant. There's always exactly one outgoing temporal edge for every character from every state. But I think what you're getting at is this idea of like, how many wrong beliefs are there? Like, how many different versions of reality do we have to keep track of at every moment? And yeah, I agree. That would be super interesting. It's one of the things we want to explore. You know, is narrative planning harder when you have to keep track of a bunch of versions of the real world? Yeah.
All right, that's it for this presentation. Thank our speaker once again.
Right.